Hi, my name is Justin Huntington, Research Professor of Hydrology at the Desert Research Institute. Today I'll be talking about an exciting project called OpenET. So every day, thousands of people across the West make decisions about water. Farmers, local and regional water managers, and state and federal planners. And with water supplies becoming increasingly scarce, many of them are being asked to do more with less. This makes good data and information all the more important. However, many decision makers currently lack a source of consistent, timely data on one of the most important pieces of information for water management, the amount of water that is consumed by crops and other vegetation. OpenET is working to fill this data gap. This presentation will provide a preview of OpenET, which is developing an operational system for mapping field-scale evapotranspiration and making that information easily available to water resource managers and agricultural producers across the West. When OpenET goes live next year, it'll provide data at daily, monthly, and annual time steps and at spatial resolutions of 30 meter by 30 meter or 0.22 acres per pixel across the Western U.S. I'll begin with a brief overview of OpenET, describe results from Phase 1 of the Intercomparison and Accuracy Assessment Study, and conclude with an example of the Data Explorer user interface shown here. OpenET is a collaborative, community-driven effort involving more than 40 scientists and software engineers with experience and expertise in satellite mapping of evapotranspiration, high-performance computing, and data visualization. The team includes scientists and software engineers from 3 federal agencies, 6 universities, the Environmental Defense Fund, Google, and Habitat 7. OpenET is bringing together many widely used approaches for satellite mapping of ET to develop an operational system that provides accurate ET data across the Western U.S. and ultimately all of the contiguous U.S. OpenET is being developed to support a wide range of water resource management applications. First is to allow for the development of improved water budgets so that decisions about water allocations in a local basin or watershed are based on a clear understanding of current and historical uses. ET data also enable local water managers to develop incentive-driven conservation programs driven by real data that can be used to properly credit participants for real changes in water use. Similarly, the ability to track water use in near real time also significantly reduces the transaction costs for water trading programs. Finally, there are applications of ET data at the field scale, where ET data can be incorporated into range management and other irrigation management software to maximize crop per drop and reduce costs. OpenET has taken a user-driven approach, and development of the platform Data Explorer and Data Services has been informed by 12 use cases across the West. Use cases include applications of ET data for groundwater management, irrigation scheduling, watershed management, regulatory compliance, and water trading. The Diamond Valley use case, where we are comparing OpenET to groundwater pumping records, estimating historical consumptive use, and comparing these estimates to previous estimates of consumptive use. OpenET uses publicly available satellite and weather data as inputs into the system, along with publicly available field boundaries to calculate summaries for millions of agricultural fields across the West. All of the satellite-driven ET models are implemented on Google Earth Engine, which provides a shared cloud computing platform for production of ET data using the ensemble of models. Results are stored in a geodatabase and accessible via the Data Explorer user interface and also an application programming interface, or API. The API allows for automated retrieval of data from OpenET to facilitate integration with other software systems, including irrigation scheduling software tools, farm and ranch management software applications, local, state, and federal water data information systems, and water trading and accounting platforms. We recognize that for many applications, ET data is most powerful when it is combined with other sources of information, and this is especially true for irrigation management. Irrigators have to account for other factors including fertilizer and pesticide management, harvest dates, and coordination of activities across dozens of fields or irrigation blocks. OpenET will allow farmers and irrigators to access ET data directly from OpenET or via other farm and range management software they may already be using. In the past, the availability of ET data from different providers and models has been a source of confusion for practitioners, and even a barrier for more widespread use of ET data in water management. To address this challenge, OpenET is taking an ensemble approach. The team is bringing together multiple models that have been used operationally by state or federal agencies or are advancing toward operational use in the Western U.S. The team is comparing them to understand and explain the similarities and differences, and then taking advantages of the strengths of each model to generate a single number from the ensemble that represents the most accurate estimate possible for each crop or land cover type, season, and region. OpenET is driven primarily with Landsat data, which provides information at a resolution of 30 meters, but also incorporates data from other satellites such as NASA's Terra and Aqua and NOAA's GOES satellites, and the European Space Agency's Sentinel-2 satellites to provide a robust set of inputs to support reliable data production across the Western U.S. OpenET is currently conducting the largest intercomparison and accuracy assessment to date for satellite-driven ET models using data from flux tower sites, publicly available groundwater pumping records, and watershed-scale water balances previously compiled by USGS. The team is comparing satellite-based ET data to ET data from over 150 flux towers across the U.S., covering a wide range of crops and land cover types. In addition to quantifying the accuracy for each individual model, the team will use the results from this analysis to identify the best performing models for each crop type and vegetation type, and will use only those models to calculate the final ensemble value. OpenET has conducted rigorous quality assessment and quality control of the flux tower data and assessed energy balance closure for nearly 260 Ameriflux sites. We selected sites for which the average energy balance closure ratio was greater than 0.75 during the growing season and greater than 0.6 during the non-growing season. The team also assessed multiple footprint sizes from 90 meters by 90 meters up to 210 by 210 and assessed each site to ensure the footprints contained representative areas and made adjustments for wind direction if required. In addition, the team conducted dynamic footprint analyses with the Clune footprint approach. For many of the models, this is the first time they've been run on Google Earth Engine over an area the size of the Western U.S. Because of this, the OpenET team has taken a two-phased approach for the intercomparison. 40% of the flux tower sites are used in phase 1 to allow the teams to identify and address issues in automated implementation of the ET models, and 60% of the sites are being held back for a final blind intercomparison in phase 2. An example from the phase 1 results are shown here for an almond site in California. The scatter plot on the left shows the agreement between the flux tower ET on the x-axis and the satellite-based ET on the y-axis. For most of the models, we see very good agreement with slopes for the best fit line between 0.92 and 0.99, indicating very little bias, with root mean squared error values of between 0.5 and 1 millimeter per day, and R-squared values all above 0.9. The time series chart on the right also shows excellent agreement of most models against the flux tower data, where most models are within the range of the flux tower station closed and unclosed energy balance estimated ET. The results from phase 1 are highly encouraging, both for irrigated agricultural sites and other land cover types. Here's an example for an alfalfa field in southeast Oregon in the Malheur Lake Basin, which is part of the Great Basin. The graph on the left shows the comparison of ensemble mean OpenET estimates with the eddy covariance station estimates of ET. In general, OpenET shows good agreement to the station data, where data points fall close to the 1-to-1 line, and many are within the uncertainty of the station estimates, as shown by the gray shading. The graph on the right shows the monthly time series of OpenET estimates shown in red, with eddy flux station ET estimates shown in blue, with the shading indicating the station uncertainty in ET. The gray vertical lines identify satellite overpass image acquisition dates, and the green vertical lines identify alfalfa cutting dates. Notice that OpenET generally tracks with the station-based estimates even during cuttings and harvest periods. Overall, the phase 1 results are highly encouraging. For cropland sites, the average annual ET values for the models are within approximately plus or minus 10% of the ensemble mean as shown in figure 1. And almost all the models fall within the range between the mean closed and unclosed energy balance corrected ET for the flux tower sites as shown in figure 2. Key summary metrics are shown in the table, and the slope of the best fit line for all models is close to 1, with the mean absolute error and the root mean squared error values between 0.5 and 1 millimeter per day, and R squared values between 0.8 and 0.91. These results are just for phase 1, and we expect these metrics to improve slightly after the teams complete the final versions of the models this month, and we start on the final blind intercomparison study. It is important to note that models are not being tuned or calibrated to any of these sites, and of course they are not assimilating any data from the validation sites either. Interestingly, the ensemble value performed as well or better than any individual model during phase 1 and had the lowest mean absolute error and root mean squared error values. The OpenET Data Explorer will provide access to ET data for millions of fields across the West with just a few clicks of a mouse. The system currently has about 3 million fields, and the geodatabase stores over 4 billion data points. And once we extend the data record back to 1984, the start of the Landsat record, the geodatabase will store over 100 billion data points. The Data Explorer allows the user to select different years, switch between millimeters and inches, and the colors on the map correspond to the ET as depth of water in inches or millimeters as shown here in this legend. In addition to the field summaries, data is also available at the original satellite spatial resolution of 30 by 30 meters. To show you how it works, I'll go ahead and zoom into Diamond Valley. As we get to about zoom level 12, the system's now loading the data into the browser, and just by placing the cursor over the field, the time series of monthly ET is shown for the selected field. The acreage and crop type are based on publicly available sources, which for Nevada includes both actual places of use, field boundary data available from DRI, and data from the USDA Cropland data layer. Clicking on a field will retrieve the time series of ET data for the year selected. Data is available for the ensemble value and for each individual model. The grower associated with this particular field has had well yield issues over the last 4 years, and we can clearly see reduced monthly ET due to reduced pumping. Clicking over the cumulative tab, we can see how the annual total ET for this field has reduced over the last 4 years. Similar results can be seen in areas where water conservation programs have been implemented. Providing shared access to the same information for growers and water managers is really important to advancing innovative and new water conservation programs at scale and in ways that also help sustain agriculture across the West. And again, the data is available for every 30-meter pixel, so if there's a region of interest outside of the current field boundary data sets, that data can also be retrieved. OpenET will go live in spring of this year, and please don't hesitate to reach out to me if you have any questions or recommendations for the team to improve the value and utility of OpenET for water management in Nevada and the Western US. Thanks so much.